One thing to also be aware of, this is our last piece. Sometimes you'll encounter limits where you have two parts added together or two limits multiplied together or something like that. It's good to know these rules. Basically, the general idea is if it makes it easier, limits can be split up. The most critical one, limit of f of x plus g of x, is a limit of f of x plus the limit of g of x That's the same as the derivative rules. This one is not. The limit of f of x times g of x is a limit of f of x times the limit of g of x. Basically with these is just anything that you have, you just stick another limit in there and you're good to go. But it's not the product rule, it's its own special thing. So don't mess up the product rule just because I'm showing you this one. Yeah. Limit of f of x over g of x, likewise. Again, not the quotient rule, so don't use this when you're doing derivatives. It only works for limits. And a couple where k is a constant. Limit of k times f of x. This one is like the derivative rules. K times the limit of f of x. And also the limit as x approaches some letter c of k, where k is a constant, is just k, because there's no x for us to plug in for. So when it comes to doing problems, here's an example one. Limit as x approaches 0, sine x over x plus 3. This, when we put in 0 over 0, we're going to get division by 0, and this is going to be 0 over 0, so it's going to be problematic. And normally we want to do some sort of like factoring or something like that. But there's this plus 3 running around, and it's kind of icky, and it could cause problems. So the nice thing with this is to know that we can just look at these completely separately. So, separate them, don't worry about them. Looking at this one, we have the indeterminate form, so we can use L'Hopital's rule. And this one, there is no x, there's nothing to plug in, the limit is just 3. Derivative of sine is cosine. Derivative of x is 1, and the plus 3 is along for the ride. Cosine of 0 is 1. 1 plus 1 is 4. One more example. These limit rules aren't quite as super necessary when we're just plugging in, canceling, evaluating, that kind of thing. I think we tend to do them fairly automatically, just short of using them, because it makes a kind of intuitive sense. This is most useful when you have part of it that you need to use L'Hopital's rule on and part of it that you don't. So for example, let's say that we're taking the limit as x approaches infinity of x over e to the x plus 1 over x squared. And the thing is that if we put in these infinities, it's really unclear what we're going to end up with, because we've got infinity in the denominator, we've got infinity in the numerator and denominator again, and all that kind of thing. So let's split this up into 2 of them and see if that makes life any better. Because we have a lot of tools for working with things that are in this form, where it's just something divided by something else. And if we can separate them out, then we can just do this part and this part separately. So over here we've got infinity over infinity. We don't have a good way to cancel that out or circle the biggest one and see what it divides out to be. No luck. So we can use L'Hopital's rule on that one. But this one over here, we're just saying that we've got 1 divided by a very, very, very large number in the denominator. And we know from our rules earlier back in limits 3 that a number divided by a very, very, very large number approaches 0. So over here we've got limit as x approaches infinity, 1 over e to the x. This has become 0, and lo and behold, now we can look at this and see this is also going to become 1 divided by a very, very, very large number. So it's also going to become 0, and there we go.